The next reaction in this chapter is hydroboration-oxidation. In this reaction, we're also adding H and OH across a double bond, but this is a method of obtaining anti-Markovnikov regioselectivity. So in this case, we have a double bond where we have a less substituted vinylic position here, and we're going to put our OH right there. So this results in anti-Markovnikov addition. So our reagents for this reaction are, quite a few here. We've got BH3, which is borane, THF, which is tetrahydrofuran, H2O2, which is hydrogen peroxide, and NaOH, which is sodium hydroxide. So notice that this is a two-step reaction sequence. So first we add the BH3THF, second we add H2O2NaOH to obtain our product. So in the first step, for this reaction, our reaction is stereoselective and it's also regioselective. So remember, we've got anti-Markovnikov addition where the OH is going to go to the less substituted side, the H is going to go to the more substituted side, but it turns out that we also get syn addition where the H and OH will either add to the top side or the bottom side. They're going to either add to one face or the other face. So we get what we get is a mixture of enantiomers. So we're going to have a racemic mixture of enantiomers where they're adding either to the top face or the bottom face. Okay, so we don't get anti-addition where we would get the hydrogen added to one side and the OH added to the other side. All of the products that result from syn addition. So let's kind of write down what we've learned here. For this reaction, we're adding H and OH. We're adding those with anti-Markovnikov regiochemistry, and our stereochemistry is syn. Alright, so borane, or BH3, is very similar to a carbocation in that we have this empty p orbital that can accept a lone pair of electrons. And that's because borane is not very stable because it doesn't have a full octet. So since boron, in this case, does not have an octet, okay, it undergoes this intermolecular reaction in order to stabilize itself, where we end up with this kind of resonance hybrid here where the borons are sharing 2 electrons between them. Okay, the boranes are sharing 2 electrons between them in order to stabilize the system. So we want our free BH3 for this reaction. So in order to obtain that, we stabilize the borane with tetrahydrofuran, which is this species here, and it's abbreviated THF. The reason it's called tetrahydrofuran is because this thing here with the 2 double bonds is called furan, and if you remove those double bonds, then you got to add 4 hydrogens around it to get the double bonds off of there, and so that's why it's called tetrahydrofuran. It's just a common name for this molecule. So this stabilizes the borane by donating a lone pair of electrons into that empty p orbital. Okay, and so what that's going to do is form this zwitterionic species over here on the right, which has positive and negative charge within the same molecule, and that stabilizes the BH3 so it can react. Right, so in the first step of this reaction, the alkene is acting as a nucleophile to attack the boron. Okay, remember that that empty p orbital is subject to nucleophilic attack by this alkene. Okay, and at the same time, the alkene is forming a bond to the boron. The boron is transferring a hydrogen to the more substituted side of the alkene as a hydride with the 2 electrons that were on the hydrogen. So the boron is attacked by the less substituted side of the alkene for a couple of different reasons. First of all, the less substituted side has more room to attack the boron. And second, as that positive charge is building up, it's more subject to build up on the more substituted side of the alkene. So as that charge builds up on the more substituted side of the alkene, the hydride is transferred from the boron to that more substituted side, so we get this intramolecular species as a transition state. And in our intermediate product here, we have the hydrogen transferred to the more substituted side, and the boron is transferred to the less substituted side. Okay. Now this happens for each boron. This is going to happen with 3 alkenes. If this, what was our alkene here, is considered an R group, so for organic chemistry we call something with carbons an R group, we do that 3 times for each boron, so that we end up with, instead of BH3, we now have BR3, where our R is what was our alkene here. Okay, well, I'm sorry, I should circle the whole thing, but instead of an alkene, we don't have the double bond anymore. Okay, so that's what was our alkene is transferred to the boron, and that happens 3 times so that we get that BR3. Okay. Alright, and again, that happens in this fashion, in anti-Markovnikov fashion, because the less substituted side is better able to reach the boron, and the hydrogen is then transferred to the more substituted side. Alright, and so this transition state for the anti-Markovnikov addition is lower energy than the Markovnikov addition because the less substituted side is less crowded than the more substituted side. Okay, and so over here we've got a higher energy transition state. So the BH3 transfers to the, or the boron, I'm sorry, transfers to the less substituted side. The hydrogen as a hydride is transferred to the more substituted side. Now, what we have is this BR3 group here. Sorry, I thought I had turned my phone off. Alright, so now we have this BR3 that we just formed, species, and we got to get the R's off the boron. So remember our overall reaction here was, in our first step, we have BH3, THF, and our second step, we already did that part, right? And then our second step on our reaction arrow is H2O2 and NaOH. Okay? So our second step is to get the R's off of the boron and to put an oxygen between the, on the R's and to put our OH group rather on there. So we're going to take the R's off the boron and add an OH group to those R's. Okay, so this is the mechanism for doing that. It's very complicated, and I wouldn't expect my students to remember this mechanism, but your professor may want you to remember that. So we have sodium hydroxide in the presence of hydrogen peroxide. The OH group from the sodium hydroxide can deprotonate the hydrogen peroxide to form this hydroperoxide, which is a very reactive species, which will now attack the boron of the BR3, and when it does, it shifts an R group over onto an oxygen and kicks out the OH here. So now we have this OR attached to the boron, and that happens for each one of the R groups, so that we have this trialkoxyborane, where we have B and then OR. Okay, so when we form that, the next step is a hydroxide attacks the boron, and when it does, it kicks out one of these ORs. Okay, and that OR can then pull off a hydrogen from water, giving us our alcohol. So that happens for each one of those R groups, so that we end up with an OH added to that less substituted side of what was the alkene. So for each one of these, we want to predict the product. So for A, we've got this. So what are we adding and where are we adding it? We're adding H and OH in anti-Markovnikov fashion. Okay, we also have syn addition, but for all of these problems, we don't have to worry about that because we're not forming a chiral center here. So this would be our product. So we added H to this side and OH to this side, right? So this is our product. So for B, we've got this product, okay? We added H and OH, anti-Markovnikov. And for C, we've got this product. And none of these formed a chiral center. But if we do form a chiral center, we mentioned earlier that we have not just regiochemistry to worry about here, we have stereochemistry as well. This reaction is stereospecific in that we only get syn addition because the H and the boron add to the same face at the same time, and removing that boron does nothing to disrupt that stereochemistry that formed when it added, okay? And so we get H, essentially H and OH, adding to one face or the other of what was the alkene. So in this case, we formed one chiral center. So the OH can either be, on the top or the bottom here as it's drawn. So in other words, we're forming a chiral center here, and we get a mixture of enantiomers. So we could draw that like this. We could say that the OH is coming out, or the OH is going back. Or we could have just drawn one of them and write plus En for enantiomer. So we're going to get a racemic mixture. Now, if you form two chiral centers, which is possible if you have a species like this, again, what are we adding and where are we adding it? We're adding H and OH in anti-Markovnikov fashion. Okay, and we're getting syn addition. So what does that mean? It means the H is going to this side. That's the more substituted side. The OH is going to the less substituted side. They're both going to the same side at the same time. So in this case, we form two chiral centers here in this product, and we have to indicate that in our product. So if we draw this correctly, we show that either the H is going back and the OH is going back, or the H is coming out and the OH is coming out. So notice that we form a pair of enantiomers here because we form two chiral centers. We don't get the alternate possibility where, say, the OH would be going back and the OH would be coming out, where the H would be going back and the OH coming out. I mean, you can't have those on opposite sides. So let's consider this product here. What would we get? So we're adding H and OH across the double bond, anti-Markovnikov fashion, and syn addition. Okay, so what's our product? Okay, now the OH is going to go to the less substituted side. The H is going to go to the more substituted side. So that means if the methyl group that's already on there is coming out, then the H is going to be going back. So the OH also has to be going back. And then we can have the OH coming out. And that would mean that the H would also have to be coming out, and the methyl would have to be going back. So notice here that these are not enantiomers because we had this methyl group. Circle that in a different color here. These are actually diastereomers of each other. They're not enantiomers. Okay, so we get a mixture of diastereomers. Okay? But we don't get the situation where we would have like the OH, sorry about that, I thought I had those turned off, where we'd have the OH going back and the H coming out. I mean, but they're still syn, but because we had this other methyl group here, we get diastereomers in this case. So let's work these problems before we move on to the next section. Okay, so for all of these, what are we adding and where are we adding it? We're adding H and OH, anti-Markovnikov, and we're adding those syn. Okay? So for the top one, we've got, if our methyl group here is coming out, I still have trouble writing with this, then the hydrogen's going to be going back, and the OH will also be going back. And so did we form a chiral center? Yes, we did. Both of those are chiral centers, and so we could write plus En in this case because we didn't have diastereomers because we don't have any other chiral centers in the molecule. But it might be better to just go ahead and draw it in, just to make sure. So if the OH is coming out, then the H also has to be coming out. Then the methyl group would be going back. Okay, so both of those are possible. So for B, our next one is we're going to add the OH on the less substituted side, so that's going to be over here. The H is going to be on the more substituted side, so that would be like that. So what does that mean? This is pretty complicated. That means that this group would have to be coming out at us, right? Yeah. All right. And then we also would get the other product where they're both going back. I'm sorry, they're both coming out. The H is coming out and the OH is coming out, right? Okay, so C would be here. We've got the OH is going to be on the less substituted side. The H will be on the more substituted side, but that's not actually a chiral center, either of those. So you can just draw the lines, okay? So we don't have to worry about whether the syn addition here. Okay, thanks for watching. I'll see you as we continue addition reactions.